All right, so that brings us to descriptive statistics. So we have a bunch of numbers here, but they don't really mean much unless we figure out how we can talk about them and how we can relate them to other pieces of data. So set numbers meant to help determine central value or tendency is how far the spread is. So central tendency is the indicator at the center of the data. And this could be any number of things. It could be the middle temperature. It could be the middle weight in birth weights. It could be all kinds of data. All right. It's the number that shows up the most, or it's the one that's kind of in the middle there. So for example here in nominal data, it's the mode. So 5, 13, 9, 7, 1, 9, 2, 9, and 11. We have 9 3 different times. So even though 9 isn't really in the center of this data point, it is the most used, and that's what the mode is. So the mode is the most frequently used observation. Okay. Bimodal means the sample has two modes. Let's say we had a whole bunch of 7s in here too. We could have a bimodal sample, and then multimodal is more than 2. The more modes that you have, the less information a mode actually gives you. So a median is for rank ordered data only. You can't have a median in nominal data, for example. There is no median between a male and a female. There's no median between an Abigail, a Sean, and a Emily, okay? It has to be a rank-ordered object for it to exist. So you line the data up from the least to the most, and then the middle number is the median. Sometimes that's easy. In an odd number set, the middle is just plain the middle, right? We have 3 on this side, we have 3 on this side, so 6 is the median number. In an even number, we can turn that even number into an odd number by adding the 2 middle ones and dividing by 2. So here we have 1, 2, 3 on this side, we have 6, 8, 9 on that side. We take these two, add them together, divide by 2, which is actually an average, and we come up with our median number. So speaking of averages, that's actually called the mean in statistical speak. So that's all numbers added up and divided by the times that it was measured. So for example, if we have 4 people that took a test, one of them got a 97, an 88, a 94, and an 85. If we add all of these up, divide by 4, because that's how many tests we had, we get our average. You guys have been dealing with averages for a very long time. But what's interesting about statistics is that in a normal distribution, this is also called a bell curve, this is how things should distribute typically, okay? The mode, the median, and the mean turn out to be pretty much the same. When we have skewed data, the mode, so the number of same findings, versus the median, which is really the middle number, versus the average of that number are totally different. So we see that, for example, on if we had 4 test scores and one person scored a 28%. It drags the whole average down, right? The same isn't necessarily true if 2 people got a 100% and somebody else still got a 70 or a 50%. We don't see that mean changing as much. So that's why you can have skewed data on one side or the other. So we also have a range and a standard deviation. So the range is the difference between the maximum and minimum value. So for example, here we maybe have the number 5, and this may be the number 10. There's not a lot of numbers in between those two. Whereas here maybe we have the number 0 and we have the number 100. So both of these are bell curves. Both of them are going to have statistically about the same deviations, but they have a smaller scale between them, or a smaller range. The standard deviation is the average distance of the values from the variable's mean. Okay, so the mean again is the average in the middle. Both of these are bell curves, so we're assuming the average is in the middle. When the deviation is large, it means the sample didn't have a lot of commonalities. Okay, when it's small, it means the sample was pretty similar. So this is a small sample between 0 and 5, and most of the stuff inside of it was pretty much the same. So if this were grades, for example, we would only have maybe 5 or 10 people who took the study or took the test, and most of them scored right in the middle here, and there's not a lot of people who got a 100% out here, or a lot of people who failed it over here. So the results are pretty much the same. In a large standard deviation, we still have that bell curve, and this is what most classes should look like, right? One person down here probably failed it, one person up here got a 100% on the final, and most people are in the middle here. And we're going to talk about what those deviations mean later on down the road. So to calculate the standard deviation, there's a lot of math here. I don't want you to panic about the math here. At no point in time in this class am I going to ask you to calculate a standard deviation. FYI, if you ever do have to calculate a standard deviation, Excel will do it for you, and so will the internet. So Google. But essentially, it's the mean subtracted by each number of the sample and then added together, and then divided by the number of members in the sample minus 1. Okay? Then we get the square root of that answer. Yes, that's complicated. Again, the key here is not that you understand how specifically to do the math. It's that you need to understand where a standard deviation comes from. That we took the data that we had, we subtracted each number in the sample, we added it all together, divided that information, and the square root of that gives us how far away each piece of our data is. Okay, so for example, here's a standard deviation. So this is, again, a regular bell curve. It makes a difference when your data is skewed. So we're talking about a regular bell curve. We definitely maybe had more than others here, and we definitely have less than others here. So the average, the mean number, is in the center here. So if we stay on with our grade continuum, if the average score on the test was 75%, let's say, not a great score, right? But if the average score was 75%, then about 2% of people are going to get a 100. Okay, and on the other side of that, about 2% of them are going to fail. Let's say 50%. Okay, so the probability of kind of being in that zone here is about 14%. About 34% are going to score just a little bit underneath that 75% mark. About 34% are going to score a little bit higher than 75%, and a smaller number of people are going to score higher than the next deviation, and then the smallest number of people are going to score really high. Okay, so the standard deviation tells us how much above or below the mean score the person scores. Okay, we can also see this on a whisker plot. So remember, on the whisker plot, we have the smallest sample value, so the lowest score of the test, to the largest sample value, which is the highest score on the test. We have a median number in there, which was our 75% on the exam. And we know that a certain percentage of people are going to score higher than that, certain are going to score lower than that, and it's going to depend on what our deviation is as to how many percent of people that is. Okay, so the whole point of having a test is that you want a bell curve here so that you know, statistically speaking, a certain percentage is going to pass and a certain percentage is not going to pass. And then, of course, your job as a student is to make sure that you're in the percentage of the ones that pass. We also have inferential statistics, which is the probability that chance has a particular outcome. All right? There's always room for error. Nobody will ever tell you that in inferential statistics you have a 100% reliability rate. Right? So we do have a frequency distribution, the number of times something occurred. You have a probability distribution, which is the probable time something will occur. This is a fact. This is the number of times something physically happened. So if we evaluated hand washing for 100 times and 94 people washed their hands before they went into the room, that's a frequency distribution. We know that number is factual. The probability distribution is expanding upon that with math. So we know if that was our sample, if we project the answers outwards, we can say that in the future, probably about 94% or 97% of people will wash their hands before they go into the room. So the p-value is the probability of finding an outcome that you actually observed. So a low p-value means you are not likely to find those test results. So say, for example, we had just done some education about hand washing. So when you did your frequency distribution in your experiment, you found that people were 97% compliant. A low p-value means that you're not likely to find that again. So say you wait 6 months and you measure again, and now you only have 50% compliance. All right, you have a low p-value. A high p-value means you're very likely to get the same results every time you do the experiment. So if you said 97% the first time, you're going to get maybe a 96% the second time, maybe a 97, but it's going to be very similar to your first results. So it's based on a true null hypothesis, and a null means there's no relationship between the dependent and independent variables. Okay, so null is a little bit confusing. Null basically means the thing that you're trying to prove is absolutely false. Okay, we want to reject the null, meaning whatever we said we're trying to prove is true actually is true and not false. Okay, researchers want a low p-value because it makes them more likely to reject the null. So your book's example is actually the movie Mulan. So because there's always room for error, we have to account for error, and we have to decide as researchers how much error we're willing to put up with. So if you've ever noticed in a news article, there's that little plus or minus 1, 2, 3 as a standard deviation. That is your percentage of error. That's your P. Okay, that is telling you, yes, this data was true, but I have a 10% chance of being wrong. Versus, yeah, this data was true and I am 99% right. So in Mulan, if you said that every soldier in that army was a male, you would have a pretty high percentage of being right. But Mulan was pretending to be a guy so she could save her dad. So you're not statistically 100% right, right? You have a room for error. Every single thing you do has room for error. So we just have to evaluate how much error is reasonable and how much is not, depending on the study. That also brings us to frequency versus probability. So frequency is how many you can do. Probability is if you kept going. We kind of talked about this already. So for example, you roll a die or dice 1,000 times. You end up with a frequency distribution. We know for a fact what your answers were when you kept rolling that dice. Probability tells you what that distribution looks like if you could keep going. So I can't, or I don't want to, sit here for another few weeks and roll the dice 10,000 times. I don't want to do that. I just want to do a future estimate, which is exactly what probability is. So how likely is your patient to get diabetes? That's a frequency estimate. That's a probability. So we can take very basic information like their A1C and their resting glucose levels, and we can estimate how likely they are to develop diabetes in the future. So we use this all the time in nursing. Same thing for an inhaler. How likely is this inhaler going to work? If you have tested it on that patient and it hasn't worked previously, probably not going to work this time. That's an estimation of the probability of something. So again, normal distribution is typically on a bell curve here, and that's the probability of distribution in which the mean, median, and mode are equal. It is not a bell curve if this line here, which is the mean, the median, and the mode, is not the same. Okay? In a large sample, the bell curve is accurate. In a small sample, the bell curve is not always accurate. If I talk to 10,000 people about something and it falls on a bell curve, I can be pretty sure that my results are accurate. If I talk to 4 people about something and it's on a bell curve, that's not enough of a sample to make reliable results. So the more random variables you add, the more likely you are to end up with a bell curve. So if I can talk to 10 people, that's an okay study for a small scale, but what I really need to talk to is 100,000 people. So probability helps us with that in some aspects, but sometimes we need to create bigger samples to create a more reliable distribution. Right, we've already touched on this just slightly, but this is skewed distributions. So skewed samples are due to significant numbers of outliers. So for example, one person fails the test. All right, again here we have less people who scored high and one person who scored kind of low. Or maybe we'd be down here. One person failed the test and most people did pretty well on it. This, for example, would be most people did not do well on the test, and one person got 100%. Okay, so our mode, our median, and our mean are not the same. For example, one person died from a procedure. Okay, or actually this would be up here. So if the risk levels of procedure, one person died. That's a high risk versus most people who didn't. So we have a skewed plan here. right? Z-scores tell you how many standard deviations the observation is from the mean. A bigger Z means it's further away from the rest of the data points. So if you recall, a standard deviation is all that big math stuff that gives us a number as to how far apart our variables are. So since we've determined how far apart our variables are, we can actually mathematically determine these outliers. So if this person scored a 100% and everybody's scores was 2 points away from each other, then I can say that they scored 10 or 15 points higher than everybody else. So that's what a Z-score gives us. All right, we'll be back for measuring data.